My name's Christina, and I'm part of a team of undergraduates trying to develop a serious game to solve an NP hard problem. Okay, so just for some context, serious games are games that engage people to perform some kind of task as a byproduct of playing them. In particular, they can be used to leverage human abilities to solve computationally intensive problems. And this is motivated by two reasons. The first is that people are smart, so they can solve difficult problems. And the second is that people love to play games, so they will spend lots of time playing them. These are some examples of some successful serious games. There's Peekaboo. It's an image classification game used to train computer vision algorithms. Galaxy Zoo is also an image classification game, but it's used for classifying galaxies. And Foldit is a protein folding game for looking for the underlying structure of various proteins. The problem that we are focusing on is called n-way matching. It's an important problem in software engineering. I don't have time to explain why, but the problem basically boils down to the need to identify similar elements from multiple inputs. So here on this slide, there are 3 inputs, X, Y, Z. Each input has elements, and each element has attributes. The goal of the problem is to look for and group together elements that share common attributes. An optimal solution is where the grouped elements have the most similarity. So in this example, one way you can group these elements is to match the ones joined by the dotted lines. In this case, they share one attribute, and this happens to be a suboptimal solution because we can do slightly better. In the optimal solution, you would join the elements that are connected by the solid lines, and in this case, they share 2 attributes. This process of looking for an optimal solution is NP hard, and it turns out that current approaches used to solve n-way matching either take forever to compute or they produce crappy solutions. So this is why we're turning to serious games to see if human abilities can outsmart existing algorithmic approaches. In the game, we're relying on human visual cognition, so every element gets encoded by a visual game character, and every element attribute gets encoded by a game character feature, like its hair, bunny ears, or wings. In the game, the player's goal is to identify similar looking characters, and this corresponds to identifying similar elements in the n-way matching problem. So if you inspect our game characters, it becomes apparent that similar elements do indeed look visually similar. We spent about a year developing this game. We developed many versions in order to address our challenges, which include how to make the game fun, how to leverage human abilities, and also how to reduce cognitive overload, because in many of our cases, people will have to match hundreds of elements. This summer, we arrived at a working solution. We then launched a player study. So in a period of about 2 weeks, 400 people played our game, and it turns out that people are pretty good at it. They were able to beat all state-of-the-art algorithms in all of our case studies. I'm going to play a demo of the game, but if you want to check it out yourself, the link is on this slide.
For the alien at the top of the screen. Aliens from the same group will have the same colored background. The red bar below each alien indicates its similarity with other members of its group. Aliens that are similar to members of the group you are forming are highlighted in yellow. Adding highlighted aliens to your group will likely increase your earnings. If we reach the target score, we win the game.
Okay, so that's our game. Thank you very much for listening to my presentation, and I'll be happy to take your questions. And if you're interested in learning more about our project, you can come to our poster session later today. Thank you.
Good morning, everyone. I'm Farjana. Our project name is mannequin. And this is my partner, Ariana and Jocelina. I'm sure you saw the movie called RoboCop, or you heard the name of RoboCop. So that's male version of robot, and my robot is female version of robot. It's robot plus queen, RoboQueen. So a lady from a company called Global Fashion Technology Federation, she was trying to get a robot that can move and talk. So she went to Japan to buy a robot, which was more expensive, like $3,000 per robot. And those companies said they need to hire, they need to hire engineer in order to program or in order to run those robots, which was more expensive than buying a robot. So she came back and she came to us. So we built a robot, which is a very low-cost robot. Do you want to? Yeah. As you can see the robot, that's the model of the robot. So we built our robot from very low-cost material and components called Raspberry Pi, Arduino, servo motor, RPI camera, cardboard. It's like 3D model. We use 3D printer to take the printout of the 3D body. And we use LED for the lip and eyes. You might take linear algebra for your major. The students who is doing like computer science or computer engineering or math, they need to take linear algebra for our math classes. So we use linear algebra for the movement of the arm and the head part. We use Python also for the movement. And for the speaking part, we use software called eSpeak in order to make that robot so that it can interact and talk to you. Like if you go to some store called Macy's or JCPenney, you always see the static robot. It doesn't move or it doesn't talk. So our goal was to get a robot, it can interact with the customer, and then we can display our brand name clothes and brand name jewelries to the customer. But sometimes the customer, they have question, oh, what's the price of the product? So the robot can actually talk with them and tell them the price. Oh, this is $30, this dress is $30, or this jewelry costs like $5, something like that. So that's the plan of our project, like is the real implementation of education, and then for the fashion industry, for the low-cost robot. So my partner, she will explain the hardware part.
A life-size interactive robotic mannequin prototype was designed and developed low-cost open-source hardware and software with an emphasis on using readily available off-the-shelf construction material and hardware devices. So our block diagram, the main component is Raspberry Pi that connects motor controller that control 8 motors, 2 in the neck and 3 in each arm. It also connects to audio amplifier that output the sound into speakers. And we also use RGB LED lights for the eyes that can change the color, and LED that for the mouth that sync with the audio amplifier, so it's changes on the sounds.
But we're not planning to use a robotic mannequin as in the fashion industry, but we're also planning to introduce it in other areas of study and further research, such as the social robotics research projects, mobile device control programming, 3D physical modeling and design, wireless networking. We're also planning to implement it in a way that it's going to allow to the customers to interact with the robotic mannequin by using a web-based user interface through the smartphone wireless connectivity We're also planning to implement it red, green, and blue LEDs that it's gonna be synchronized with the speech of the robotic mannequin, and it's gonna be used in another areas of study and computer engineering programming courses because the robotic mannequin, it's designed and it's implemented some different software tools and computer hardware and networking communications. So it can be used to teach these topics in computer programming courses. Thank you so much, and we're open to any questions. Question?
Hi, yeah. I think your design is really cool, and I was just kind of wondering how you came up with the design and then how you basically went about creating it. So you said you used cardboard, but did you like 3D like laser cut, or like what did you do? What was the process, and did you use a CAD model? I was just like kind of curious how you guys went about it.
We designed using CAD tools, and we also used a laser cutter to cut the cardboard.
We actually used human body 3D imaging of human body, and was done by one of our professors. She actually used human body imaging, and our robot, as you see, it looks like a female body, so we used a female body for the body imaging, and then we had to use the CAD tools, computer-aided design, for actually building and cutting the cardboard pieces, and that's basically it. And also the frame of it, that's a body, and the frame of the RoboQueen is actually aluminium. It's a metal frame, so covering everything, it's pretty less expensive and very affordable, and that's basically it. Hope that answers your question.
So you said that first robot costs a lot of money. So how much did you find that this implementation ended up costing? Was it a significant decrease in cost?
I assume you're asking about the cost of building the robot. Okay, so the idea that came from was like from a woman who runs the company, as they mentioned. So she actually went to Japan and South Korea to look for the robots, and there it cost like $3,000. And when we were trying to build the robot, we estimated that the cost will be around $500, but so far we ended up, whatever we have in our RoboQueen, so far we have spent only $200 to make it. So it's even cheaper than what we expected. So it's as I've already told, that it's very, very, very affordable, and we can use that probably in all of the computer programming classes to make the students participate in the class more actively and not doze off in the back seats. That's it. And also in the fashion industry, and where you can display your clothes and stuff like that. Yeah. Anything more? Thank you.
Hello, my name is Berkay Payal. I'm a third-year electrical engineering student at the University of Maine. Today I'm going to present to you my research about determining honeybee health using RF and radar technology. My research is funded by National Science Foundation. Honeybee population all around the world declines rapidly. Honeybees leave the hive, leaving behind immature bees and queen alone, and do not come back for reasons still unknown. And that phenomenon is called colony collapse disorder. One of the most leading suspected causes of colony collapse disorder is the use of neonicotinoids, the world's most widely used type of insecticide. So why are the bees so important for us? Well, the honeybee plays the most significant role in our ability to produce the basis of our diet. fruits and vegetables. Therefore, the rapid and serious decline in honeybee population not only affects the economy, but the dynamics of the ecosystem as well. So in order to approach this problem, researchers have applied different techniques to monitor the bee activity and understand their behavior. They have inserted devices such as microphones and cameras inside the hive to monitor the bee activity, and some of them even implemented harmonic tags on individual bees to track their motion. However, these methods are not very effective since they do not produce collective results, and they can be even invasive. Our project tries to answer the following question. Can we use RF and radar techniques to monitor the bee activity and perhaps determine their health? To answer this question, we built an automated data acquisition system with Doppler radar unit and analyzed the information to extract information coming out of the hive. The RF unit we built is inspired by a radar course offered by MIT OpenCourseware and consists of a transmitter and a receiver that both operates at 5.8 gigahertz. The signal is transmitted and frequency modulated by mechanical bee vibrations emitted by bees living in the hive. And we process these frequency modulated signals to be able to say something about the bees themselves. Again, this is an automated data acquisition system constructed with 2 Arduino nanoboards. One wakes up the system every 15 minutes, and the other records the data for 1 minute. And at the end of the data recording, the system goes back to sleep mode. In this fashion, we've collected hundreds of data for a period of 4 weeks. And here's an example of the data that we've collected. So what's going on here? On the y-axis, frequency is depicted, and on the x-axis, the time is depicted. Notice the strong frequency level between 100 to 150 hertz. We know that this is not some sort of noise that's coming from the system because we detect this only when the radar unit is pointed toward the hive during certain hours of the day. We also know that this is not the bees' flying frequency because bees are known to fly with a frequency that ranges from 200 to 250 hertz. So what does this frequency really mean? We have 2 theories that are associated with it. For one, we visually inspected that this frequency level is detected when the temperature of the hive reaches a point where bees are not comfortable anymore. So they try to balance the temperature of the hive by beating their wings. That's one. And then the second theory is this can be the frequency coming from the bees standing in front of the hive ready to take off, kind of like a helicopter that heats its motor before flying. In conclusion, it is possible to monitor the bees with RF techniques, and an audio signature between 100 to 150 hertz is detected and attributed to bees balancing the temperature of the hive. Furthermore, bees are found to be most active between 6 a.m. and between 10 a.m. and 6 p.m. They work like a bank, open late and close early. Thank you very much. And if you have questions, I will be glad to answer. Yes, please.
How are you certain that RF techniques aren't invasive for bees? Because some theories are, some people speculate that colony collapse disorder could be caused by like high frequencies along with neonicotinoids.
That's a very good, thank you very much for that question. Well, the RF unit we built operates at 5.8 gigahertz, and that's an ISM value, industrial scientific band, and it operates at very low power. It's 13 dBm, the transmit power is 20 milliwatts, and we are therefore certain that it does not affect bees in a negative way. Any other questions about the system, the bees? All good? Thank you.
Hello, my name is Sage Trudeau, and I'm here to present the benefits of autonomous UAS for urban search and rescue. Unfortunately, it seems that as disasters become more and more prevalent around the globe, it's important for our response efforts to adapt and evolve in order to be able to handle these new rising situations. Currently, first responders spend a lot of time and effort laying down grid search patterns, and they often resort to local tips and many other small little things to be able to find survivors in the first 48 hours, which is very critical to a successful response. As seen in this picture, obviously a grid search pattern can be very difficult here depending on the damage to the surrounding infrastructure. Search time can be decreased and more lives could be saved if there was a better way to go about this manner. This is essentially where the benefits of UAS really come into play. We aim to create a system that allows a user to task a UAS to autonomous survivor detection through the use of cheap, lightweight, and commercially available sensors without relying heavily on user input. The system's goal is to accelerate the search process and allow first responders more time to focus on the rescues and less time spent searching. It's my pleasure to demonstrate one possibility of how this can be accomplished. In order to select options and receive feedback from the UAS, we've created a user interface that is displayed here. The UI is built as a mobile application, and it interfaces with the N1 flight controller to take over control. From this UI, the first responder is able to select a waypoint, and then this mission is then uploaded to the UAS as a waypoint mission, where it's stored on the onboard processor and is then systematically processed through that queue. As the UAS goes through this queue, it travels to each location and performs a search algorithm at the destination. And lastly, as it discovers survivors or hazards in an area, it relays that information back to our first responders in real time, thus giving them enhanced situational awareness. Essentially, when a UAS reaches a search location, it begins autonomously scanning that surrounding area. By utilizing a LiDAR system coupled with the robot operating system, commonly referred to as ROS, we are able to scan the area and determine entrances into structures in order to make its thermal search for survivors as thorough as possible. So this UAS is attempting to enter buildings. The LiDAR sends out a laser in a 270-degree scan, and this light reflects off of surrounding objects and then is returned, which we can then get a distance value from that. The result can be visualized essentially as a 2Z horizontal slice of the environment in the column of air that we're in. From this information, we are able to accurately determine distances to walls and nearby objects, and we attempt to classify these and look for the largest objects in the areas and possible gaps between them that we may be able to traverse through. After we locate the openings, we determine which opening is the largest, and then we adjust our position vector so that we navigate through this opening. We then perform a 540-degree spin to search the room that we've entered and then align ourselves to exit through the opening that we just went in. The UAS is also equipped with 10 low-resolution cameras that serve in pairs to accomplish stereoscopic imaging for collision avoidance. This system serves as essentially as a safety net that overrides flight control to avoid obstacles and prevent collisions while both the thermal and autonomous navigation algorithms are running. In addition to this, the UAS is equipped with a 640 by 512 long-wave infrared imaging camera that is incredibly sensitive. This imagery, which this is an image off of the camera shown here, is the starting point for our algorithm, and it provides the basis for what we begin working with. Essentially, first the live feed here is taken and it's thresholded to the human temperature range, and then this new image is then converted to a grayscale and Gaussian blurred to remove some of the noise, as well as get us ready for further image processing. It's then converted to a black and white frame, and all of the white pixels are connected and grouped into blobs, where we then attempt to further classify them and attempt to determine whether it's a human or not based upon the size of the blob and the shape. One of the main challenges here is that due to clothing and other articles, thermal signatures on humans can be obviously not completely consistent. And so it's very possible for someone to appear disjoint in an image once post-processing, and that would result in an algorithm failure. Some of the gaps here can be filled in using morphological image processing and by looking at different areas of the frame and comparing the frequency of blobs in certain areas. The idea here is essentially that if 2 or more roughly elliptical blobs that are large are in a certain area of the frame, we have a high probability post-processing of that being a survivor, and so we flag it as one. Upon successful identification, this is then, the UAS takes a picture of that and sends this back to the first responder so that the first responder can then visibly inspect this, easily tell whether it's a false positive or not, and we can get a response effort out and into the field as quickly as possible. I'd like to conclude my presentation real quick by thanking my team. I have a lot of great guys that work incredibly hard for me, and honestly, without their work here, none of this would be possible. I have tremendous respect for the work that they've done, and I'd like to thank them for everything that they've put in. Questions?
How do you anticipate changing your algorithm to account for debris that might be obstructing part or all of a body?
Exactly. It is a common problem. Basically, right now, if we have 2 or more like high probability like blobs, so maybe a head and an arm or something like that, we're counting that. And we are, anytime we get something that's in a heat match category, we send that back and then basically just filter through that more so that we don't have a huge mess of like false positives off of a thermal camera. But yeah, small sections are accepted.
Have you considered using like audio processing, like a microphone or something? Sorry.
Okay.
I'm
Yes.
over here. Have you considered using like a microphone or audio processing to pick up like the voice of a human? Maybe they could like shout for help when they see a drone. I feel like that'd be a natural response.
Yes, we have actually. We use an onboard processor it's essentially just a flying computer at that point. And so if we have hooked up a microphone, we could pursue that. I would say it's in the stages of joking around during research meetings of like, hey, can I yell at this drone and have it respond to me? You know, things get a little crazy when you've been working on it for a lot of hours.
Have you provided a complete solution for the control flow of the drone, or is it totally autonomous without any communication required?
Yes, so basically what happens is the operator puts in waypoints for areas for it to search, and it goes from there. The weakest portion of our algorithm, I would say right now, is essentially once we get there, determining an entrance to a space. It's a difficult challenge based upon the LiDAR, but it is definitely coming along. We are looking into SLAM algorithms to assist with that process, but the drone does fully autonomously navigate through zones.
How long is the flight times? Because I know that for like massive search and rescue, the times are the first 48 hours are important, and I guess just how long do the drones fly?
So without a payload on our UAS, we can get 35 minutes in the air. In reality, once we're loaded up with all the cameras, the LiDAR, and everything else, we're airborne for 15, 18 minutes. It does move quite fast. It'll do roughly 20 meters a second, and so it gets from point to point relatively quickly. And the idea here is that it keeps itself flying as much as possible, and is just an assistive tool to the responders. So once they're getting there, they're laying out grid patterns, and they're all in offices and everything. They just launch this thing real quick. It goes out. It's already bringing back information of where a survivor is. Obviously, it's not going to be able to find somebody under a pile of rubble or something like that. But the idea is this can find some of the rapid ones that maybe they wouldn't have gotten to because there's water in the way or large problems with the infrastructure.
Have you tested the drone in adverse weather conditions, in snow or rain, and how does it affect its performance?
we have not done snow or rain or anything water related. We've flown in some pretty substantial winds, and it holds up quite well. Just the control algorithms, it has really powerful electric motors, and they do quite well. Obviously, you would have to put in additional resources to get it to be waterproof or something along those lines. We're here to prove viability, not necessarily provide a product. Yeah.
How is the indoor climate with this drone?
Great. So the cameras that I kind of briefly mentioned here, which time limited, but the stereoscopic imaging that we use once we get indoors is pretty awesome, actually. I don't know if many people have an understanding, but it works similar to your eyes. So you have two cameras and a known distance between them, and you get a depth field of the surrounding area. And this works great once you get indoors. It's a little iffy outdoors, and it works great of like avoiding a tree or something like that. But once you have like walls and you have essentially like laid out plans, you start to get really accurate ability to map the area, but also just to stay airborne. It does very well at seeing an object and being like, whoop, nope, we got to get out of here. Cool. Thank you very much for your time.
I'm Carlton Rice from the University of Texas, Biomedical Engineering Department in the Cockrell School of Engineering. This project is also partnered with Seton Medical and several MDs. The core question that we're asking here is basically why we need to alter core body temperature. And there's actually a huge problem in healthcare right now. Lowering core body temperature is vital to pretty much any bodily functions, including organ, brain ischemia. We have strokes, cardiac arrest, concussions. There's applications with infants, and remediation of this preoperative hypothermia induced by anesthesia. So often when we go into the operating room, we put a patient under anesthesia and they go into hypothermia. So altering core body temperature prevents against infections, blood loss, myocardial ischemia. So how do we manage this? Basically, your body has a natural thermoregulatory system. These large bore shunt vessels called arteriovenous anastomoses, or AVAs. They're basically these large throughput terminal vessels in the non-glabrous or the non-hairy glabrous skin tissues, like the palms of your hands, pads of your face, your soles, your feet. They provide very, very good heat transfer over small surface area, and you can elicit high flow rates into these AVAs using heat exchangers, and circulate the core body temperature and trick your body into thinking that it's overheated when it's really not. We've conducted over 200 human trials, gotten great proof of concept data, and have 5 licensed patents and a couple companies. So this is kind of a picture demonstrating the effects of arteriovenous anastomoses when you're vasoconstricting and vasodilating the body. So this individual is very highly vasodilated. You can see heat transfer is being elicited to the hands and the face very well, whereas this individual, our postdoc, is very vasoconstricted, so they do not have that heat flux in their hands and their glabrous skin tissues as well. Glabrous skin tissues are used as a heat transfer portal. This is an athlete running some distance. You can see the hands and face are have a very high heat flux right now. It's pretty ubiquitous in all animals. It's in elephants. It's in tongues and feet and all these different cute little animals. This is basically what the physiology kind of looks like. You have a heat exchanger, and you have the nutrients coming in here, a heat exchange coming out there, and you basically have a crossover effect, similar to a capillary bed, but they can actually vasodilate 10 times capillary diameter, so because of that, they can elicit very high flow rates. This is kind of what the difference between non-glabrous and glabrous skin tissues look like. So you can see glabrous, very venous. The vasculature is much more in depth, whereas non-glabrous, very much less. This is a vascular cast subdermally of these AVAs, and you can kind of see just the very high embedding of these different vessels. The technology that we actually use to elicit this is taking advantage of this flow system by activating along the spinal cord. You can basically heat it up and basically trick your hypothalamus into thinking that your body is overheated, begin thermoregulation, and then apply the heat exchangers to the skin. So with this, you can get 50 to 70% of total cardiac output to these AVA areas, mostly. You can vasodilate 10 times capillary diameter. You can control it very fast and dynamically. It's very accessible. Your hands and feet and face, pretty accessible. There's very large surface area and density and very tremendous thermoregulatory power. So here's some data. There's a lot of data going to be thrown at you guys, so I'm just going to kind of zoom through it a little bit. But basically, you can see the difference between a glabrous area along the neck and a non-glabrous area and the rapid onset of heat transfer. Same thing with finger versus forearm. We have neck and toe. We have, this is just when the heater is applied. So it's initial application. It ramps up the blood perfusion really well. So this is actually a video. You can see if it plays. One moment. I don't know. How do I start this thing? Oh. Well, where's the mouse? Oh, there it is. It's up here. Okay. Yeah, so you can kind of see it's starting heat transfer about here. It's starting to go here. Heat transfer is continuing. And you can see by the end of the video, after applying this technique, the whole hand is heated up. And it was just in a matter of, 10 minutes or so. Okay, so this is a kind of more computational way of describing this is the cardiovascular conducance gradients and the change in the cardiovascular conducance to basically kind of just show that this works. You have polymer perfusion data that basically kind of just reiterates what I've been talking about. Kind of the future of this technology, to basically, it's very ubiquitous. It can be used in many applications, but generally it's to provide this stimulation to turn on the AVA flow and add or remove heat very safely, very easily to achieve ideal thermoregulation. Applications in military and sports and medical field are very much almost endless. So that's basically the concept. Our IP is different than most medical devices in that currently we use in the operating room something like this, a bear hugger suit or some whole body warming and cooling, and it's very impractical when you're going into the operating room because it's very cumbersome, over encumbering. What we have is just a simple neck heating and heat exchangers, and you have a little water reservoir with thermal fluid system and good to go. Set up and put down in a couple minutes. More data, same type of stuff, just cooling, temperature. I do some computer simulation of this data. We have basically a circuit model of a human, have a bunch of nodes and kind of analyze this computationally as well. So we add heat transfer through some software and kind of see if it matches what we're seeing clinically to get more data points. This is basically just showing the percent of cardiac output with esophageal temperatures at 22 degrees Celsius cooling. Just kind of seeing that cardiac output can be increased as temperature does over time. Future directions, more startup companies, more patents to be made off of this, 510Ks. Some new medical devices, materials, partnerships with different companies and organizations. We have just acknowledgement and understanding that this is patented IP and that it is used for medicine for the betterment of healthcare. And this is piloted by research NSF grants, Dr. Diller at the University of Texas, and my lab. So this is Karen Nyberg, who used to be in my lab. And with that, let's grab some questions. Howdy.
Have you tried it?
I have. Actually, interestingly enough, one of our graduate students right now is applying this for sleep studies. So we just last week signed a massive contract with a mattress firm to start working on this for sleep studies, and it is miraculous. It is awesome. Yes.
Hi there. Does it cool the same rate that it heats a person up?
It's based off of the Penna's differential equation with some different modulation of variables that are specific to humans. But generally, yes, the heating and cooling are very parallel. So yeah, I was in the military, grew up in military family, had many friends and comrades come back with blown off arms and limbs and having really big problems medically. Started looking into prosthetics and easily printed prosthetics with a company called Open Bionics. Then kind of saw that I could make a greater impact in a shorter amount of time doing some thermoreg research because the field is very important, but very low, very few people study it. All right. Thank you, guys.
Hello, my name is Perry Lomberg. I'm a third-year electrical engineering student at Northeastern University. When I was 16, I got a job teaching kids with cerebral palsy and muscular dystrophy to ski. For them, skiing was a form of therapy that was effective because it works on muscle tone and balance. Unfortunately, in New England, we can't ski year-round. I wish we could. But now I'm in college, and I work in the rehabilitation game and virtual reality lab at Northeastern University, where we work on applying similar therapies in a controlled environment. So I work as an engineer on a team of physical therapists who are investigating how skills transfer between a virtual environment and the real world. And some of the tasks in virtual reality and the real world can be shifted a little bit because the way we perceive the world around us isn't just visual. You can touch an object, see exactly where something is, whereas in virtual reality, you're sort of in this general region, and that's considered like touching something. So in order to improve skill transfer, which is what my research advisor, Danielle Levac, is very interested in, I've decided to pursue haptic feedback. So the core question of my project is, does inertial feedback increase the transfer of skills from a virtual environment to the real world task? So virtual reality is an effective form of physical therapy for several reasons. First and foremost, it increases motivation and active engagement, which is important for learning and being invested in a task. I know many people who've gone through physical therapy, they go home and they don't do their exercises. But if we can provide a more engaging way, that increases the number of repetitions that somebody will do on their own time. It also permits us to increase patient-specific opportunities. So say you have a geriatric patient who used to love golf, and now they can no longer get out to the golf course. We can provide them an environment that looks familiar to them and is something that they really love. In a study that we recently did that you can see an image there was for stroke patients, and what you needed to do was shift your weight and reach up to an object. And the real world task we are training for is like putting a book on a shelf. So we designed a bookcase where you have to pick up an object and shift your weight, reach up, and put it on the shelf. And what we found that was people who trained in the virtual reality environment had a lower weight shift because they didn't feel the weight of the book in their hand. But they had shown more repetitions over time when they were practicing in this environment to somebody who held a weight, shifted their weight, reached up. So what I've decided to introduce was haptic feedback. Haptic feedback can be very simple. It's any form of touch in a virtual environment. So when you're typing on your phone and there's a little vibration giving you feedback, that's a form of haptic feedback. So it increases sensory feedback, and the form that I used for this is called inertial feedback, and it can also be used to add challenge into the situation. So inertial feedback is a resistance to movement in any direction. The design I use is based off of the ExoGo exoskeleton structure. It is a lightweight design, custom 3D printed for the patient using a 3D scan of their body. Currently, we're just working on upper body single limb systems. It's lined with a soft fabric and equipped with potentiometers to measure the joint angle, actuators to provide the feedback, and 8 sensors for an electromyograph, which can determine whether or not they're actively moving that muscle or if the exoskeleton is doing all the work for them. A Raspberry Pi takes the input from the systems and determines how much force should be applied dependent on the therapist input, what's occurring in the virtual environment, and how much effort the person is actually putting into, the exercise. So the environment that I've developed takes place underwater. You can see an image of the environment up there. This is an active video game, so they're not like wearing a head-mounted display. We use this for types of proof of concept or for people who don't have a fancy virtual reality display at home. You can just do it on a computer. And since it takes place underwater, our system provides resistance in every direction of movement. So it feels like they're moving through jello or honey. And so it adds resistance training, which builds up muscle. It can record and repeat emotion. So if they're having trouble and struggling, we can just move them through the motion so they can get used to the feeling of it. And the point of physical therapy is to achieve that functional task level. So we can isolate certain joints and move them as necessary. And as we move on to clinical trials, we remind ourselves of that project question: does utilizing inertial feedback work on increasing the amount of skill transfer compared to people who have not used it? Just some of the challenges that we've run into: how are we going to tune the motor strength, synchronize it with our virtual reality environment, make it safe? And as we go into clinical testing, we're talking about future tasks to create like keep out zones. So if you have a virtual reality table, you can't just stick your hand through a table because you wouldn't be able to do that in the real world. And just as a finishing thought, I'd like to thank my advisors, Danielle Levac and Adam Cantor. And if anyone has any future questions for me that they can't think of now, feel free to reach out and get in touch. And I'll take any questions you might have.
Is it easy to put on?
Yes. It slides on like a sleeve. And so there's joints in it. You just straighten them out, pull it on, and line up the different joints. Anyone else? Okay, thank you.
I'm Tahia. I'm from the University of Virginia, and I'm studying computer science. So imagine our future with robots, right? Is it all gloom and doom for the industrial sector? With the election coming up, we all hear horror stories about how robots are going to take our jobs, unemployment's going to go through the roof, and how it's generally just going to collapse various sectors of our economy. But what about a world where instead of this competition that we face with robots, humans and robots can coexist? And even better, what about a world where robots can do the things that humans either do not want to or cannot do? And I'm not just talking about a single robot, I'm talking about groups and masses of robots, teams that can assemble to do the things we really need them to do. And these aren't niche robots designed for a really specific application. And while those types of robots are important, they serve a very pigeonholed purpose in a very specific field. I'm talking about robots that are designed to be generalizable. They're designed to be customizable and fit to the needs of humans when we need them to do certain things for us. The capabilities of robots are definitely here, now more than ever. Sensors are cheaper, processors are faster, and the dynamics and the controls between robots of different types are so different that two robots can do the same task in completely different ways. How can we use these really different robots with such strong capabilities in a variety of situations? Not just in the military, not just for delivery services, which seem to have a really big stronghold on the number of robots that are in our environment today, but in a variety of applications for people like you and I. And maybe that's not so important for us because we're at this great research technology conference, we've seen robot demos, but it is important for people that are inadvertently marginalized from getting the benefits of such important technologies. So let's think, I'm throwing out all of these great ideas of how robots can be used, but let's think of a really specific scenario where we can apply this type of technology. We all heard about Hurricane Matthew, right? A really powerful, deadly hurricane wreaked havoc on the East Coast. It was the most costly hurricane since Hurricane Sandy, and there was $8 billion worth of damage, $8 billion. There were fallen trees, power outages, damages to homes, and most importantly, human lives lost. While these awful natural disasters are occurring, humans have to take both proactive and retroactive measures to try and mitigate the effects of hurricanes. So what if instead robots, these teams of robots, could sense and determine when a natural disaster is occurring and amongst themselves decide and act on tasks that would help mitigate the effects of natural disasters or help solve some other type of problem. So instead of humans shingling down roofs, reinforcing windows before the hurricane, and then picking up debris and clearing roads after the hurricane, we had robots do these tasks for us. And that's the problem that I want to solve. How can we efficiently get these robots to complete those tasks while conserving time, because time is of essence, and conserving energy, and all the while playing up the attributes that they have to cater to different tasks. And that's the future that I imagine with robots for ourselves. I think everyone wants a job, so that phone call looks like it'll be in my future. Anybody else?
Sure. So, like, if you want a robot to, like, clear off a tree. Okay, this might help. Oh, it is louder. Okay. So, like, if you want a group of robots to clear out a tree, maybe they're, like, one that wood chips it, and then one's that collects the wood chips and incinerates it or whatever. But do you think it's in the near future that that'll be more cost effective than just sending out a team of people to do that? Because it won't happen unless it's cost effective.
I do think it'll be cost effective because the technology that we have in place right now is at a point where it's on the magnitude of just several $100s to buy a robot. And when you're thinking about human lives and sending humans out into these really dangerous applications and risking their lives to do these things, whereas you can easily put a robot out there, and if the robot is damaged or if the robot is hurt, you're just out a couple $100s. But if that's a human life, that's something that's much bigger at stake.
Out of curiosity, do you imagine that robots will look like people, or will they look like something else?
I think the reason why we've been moving towards humanoid robots is because we really like anthropomorphizing things. So even when I talk about robots, I always say like they, he, she, they'll work together, and I give them all of these human attributes. And that's mainly because that's what we're used to, and it's easy to think about things in terms of what they mean to us. But I don't think it's necessarily necessary or even useful to have robots that are like humans, because cars. The infrastructure of cars is heavily dependent on them not looking like humans. They're more efficient because of this differing structure that they have. So I think it's important to shift away from that paradigm of just humanoid robots and consider the applications of different types of robots that can be used for different things. Any other questions? Do you guys feel motivated about robots like me?